So the question here, does it matter how many times a root appears? Well, the answer is going to be yes. So I guess really what we're going to be investigating is how does it matter? So take a look at these 5 different examples. Notice that all of them have the same root. The number 1 gives you zeros in all of these different equations. So the root is it's 1 all the time. The question is, what impact does it have if your root is 1 a single time or twice? Now, what does it mean for a number to be a root twice? It just means that the factor x minus 1 shows up 2 times. If the factor x minus 1 shows up 3 times, then the number 1 is actually a root 3 times, once for each factor. So even though it's a single number, the number of factors it appears in determines how many times that is a root. So here's what I'd like you to do. A quick pause. I want you to graph these things. See how they look. Make a quick little sketch of each one, and then we'll reconvene here and take a look at things. Okay, I hope you did your pause in your investigation. I actually set up a slider here so that I can see what happens if you're a root once, twice, 3 times, 4 times, and 5 times. Now, in all the cases, note that we have one x-intercept. We cross the x-axis or touch the x-axis at x equals 1. That's true of all of these. Now, what's changing, though, is the shape of everything else. And it turns out there are some patterns that we're going to be able to find. So I'm going to make a very quick sketch of each one. So for the first, I didn't set up coordinate axes, so let me set up some coordinate axes. Ooh, those are terrible. For the first, it's just a straight line. Here, we had a parabola that came down and just touched. Here, we went through, but it kind of leveled off in the middle. For the fourth, we again came down and just touched. And then for the fifth, we once again went through, but kind of leveled off in the middle. It turns out that the number of times a root appears determines what happens at the intersection, whether you just shoot straight through, whether you just touch gently and go back, or whether you go through while leveling off. And you don't even have to look that hard to figure out what the differences are. The number of times a root appears is referred to as its multiplicity. And if the multiplicity is 1, you don't need to mention it. But if it's anything other than 1, if a root shows up more than 1 time, you do need to make a note of that. Because as you can see, it has an impact on how your graphs end up looking. Now, really, there are only 3 types of multiplicities. Multiplicity of 1. This would be where your factor shows up 1 time, first power, and that's going to be a case where your graph just goes right through the x-axis, straight line through. If you have an even multiplicity, and I'm going to include 2 examples here, once on this end. So what we saw was a parabola or a quartic graph that comes down, just touches, and goes back. So you have that root on the x-axis, that x-intercept, but it's a very gentle intersection. Comes down, touches nicely, goes back. The same thing can happen coming from the bottom. I don't want you to think that it's always going to be coming from the top. But same thing. Come up, touch gently, go back. This is what it looks like if your multiplicity is even. So pick any even number you want for your exponent, and you're going to see that same pattern occurring. If we pick even a big one, there you go. Now, the higher your exponent, the flatter the intersection looks. But they're all kind of this U shape going on. Your odd multiplicities. Now, because 1 is an odd number and 1 is a separate category, we're talking here just about odd numbers bigger than 1. So 3, 5, 7, on and on. What you're going to get is this S shape. And again, I'm going to include 2 examples because it could be that you come up, kind of level off and go through. Or it could be that you come down, kind of level off and go through. That is what your odd multiplicities are always going to look like. So Similar to the multiplicity of 1, your graph shoots straight through. It doesn't bounce off. That's for evens only, even multiplicities. But for 1s and 3s, 5s, 7s, you're going to go through the axis either directly or by leveling off. And again, come back here, choose some odd numbers. So a third power, we see that going through the axis, but leveling off. The higher your odd exponent, the flatter it gets as it crosses through. So if you go like a really big number like that, it looks almost squarish. It flattens off so quickly and so much. But it's still that same pattern. You come up, you go through, but you're flat at the moment that you pass through the axis. So here's what we're going to do then. I have set up here a function. I do not want you to graph this function yet. Please don't graph it. We're going to do two things. Thing one, we're going to figure out what our roots are. So there'll be a root from here, a root from here, a root from here. So at 8x, if 8x is equal to 0, divide by the 8. Okay, so that means x equals 0 is a root with a multiplicity of 1. I'm just going to make a note of that this time. Normally, you wouldn't list a multiplicity of 1. I'm only doing it now for the purpose of the discussion. Next, let's find the root from this factor. So if x minus 1 is equal to 0, that means x is equal to positive 1. Okay, this exponent means that this factor appears 2 times. Therefore, at x equals 1, this actually is a multiplicity of 2. Don't overcomplicate it. Multiplicity is just the same as the exponent. And then lastly, if x plus 1 equals 0, that's the factor, then the root is x equals negative 1, and this has a multiplicity of 3. We're actually, if you put together everything we have talked about in this section, you can now make a sketch of what this graph looks like without even having a Desmos or a calculator handy. Here's how you do it. I know that we have at x equals 0 a root. That's an x-intercept. At x equals 1, there's going to be an x-intercept. At x equals negative 1, there's going to be an x-intercept. Next, let's think about end behavior. So follow me here. Think back a few recordings ago. If I were to multiply all of this out, we can really focus just on what's happening with the front terms. So I have an 8x times an x to the second times an x to the third. What I'm doing now is focusing just on the front parts of each factor. So this x shows up twice, this x shows up 3 times, just so we can get a sense of the degree and what that first term looks like. So if you multiply all this out, the first term of whatever this expanded polynomial looks like is going to be 8x to the 1, 2, 3, 4, 5, 6. Even degree means my end behaviors are going to be the same. Positive leading coefficient means that my graph is going to be rising on the left and on the right. So my end behavior is going to look something like this. If we put this together with what we now know about multiplicities, which can tell us what things look like in the middle, we can get a sense of what this graph looks like. Here's what I mean. At x equals negative 1, we have a multiplicity of 3. Now I know that as I go to the left, my graph has to be rising. So as I go to the left, my graph is rising, but it's got to cross through here in that kind of S shape because it's a multiplicity of 3. That's an odd multiplicity. So it does something like this. Comes through flat and then goes down a little bit. Now notice I stopped because now we're going to look at what happens at this next x-intercept. At x equals 0, that's a multiplicity of 1. For multiplicity of 1, your graph's going to shoot right back up through the x-axis. Multiplicity of 1, shoot straight through. Now for this last one, at x equals positive 1, multiplicity of 2, that means my graph is going to now, because it's already going up, it's going to come back down, but not cross through. It's just going to touch and head back. Come through, touch, and head back. Notice that now lines up with what we know our right end behavior should be. So here you go. Roughly speaking, this is what this graph looks like. Comes down, levels off, has a dip, crosses through, has a hump, dips back down to touch, and then rises as it passes along the way. If you don't believe me, give it a quick graph. I'm going to leave it to you to actually now graph this and make sure that, roughly speaking, it kind of looks like this. And be a little bit impressed there with what you have. All right. So your task now, we're going to do the same thing we did in a previous recording, except this time, you're going to now list multiplicities if they exist. So finding on my roots from this first factor, if x is 0, okay, there's a root, no exponent, so I don't need to list a multiplicity. From a second factor, okay, so if 3x plus 1 equals 0, subtract the 1, divide by 3, x equals negative 1/3, there's no exponent, so this is a root just the one time. Now from back here, if x plus 1 equals 0, subtract the 1, x equals negative 1 is a root, but notice it's going to be a root 2 times. So mult2 means with a multiplicity of 2. So these are how I would describe my roots. Side question, just because I'd like you to be good at this skill as well. What's the degree? If you multiplied all of this out, what would the degree be? Well, I got x times 3x. I'm focusing just on the front terms. X times 3x times x twice. So x times 3x times x twice. That's 3x to the fourth. So this is a fourth degree polynomial with a leading coefficient that's positive. So its end behaviors would be up on both ends. That's something you can tell just by looking at the factored version of the polynomial. And that is a skill that's going to be valuable for you going forward. Okay, let's find our roots again. Tell you what, I'll just work in silence so that you can also do your work at the same time, and then we'll see if we end up agreeing with each other. Okay, at this point, if you're not finished, do a quick pause so you can finish up. So here's what we see. I've got x equals 0 occurring as a root, but it occurs twice. That exponent of 2 here means I need to list that multiplicity as 2. For the other two roots, now I say there's 2 because this has a exponent of 2. That means I need to use my quadratic formula. One of them is negative 6 plus root 31. The other is negative 6 minus root 31. Okay, so 4 roots altogether. 0, another 0, negative 6 plus root 31, and negative 6 minus root 31. So there you go. You found all your roots, listed the multiplicities. Just out of curiosity, I'd like to do a similar discussion here. If you multiplied your front terms together, you just end up with x to the fourth. So this is a fourth degree polynomial that would have rising end behavior on both sides.